So today we're gonna learn about dynamic push relabel, and like we will talk about expanded trimming. This is kind of warm up for what we want to do, like that I left off from last class, and it's still gonna use dynamic push relabel, and you'll see how and what it is. Yeah. So, wait, okay. Let's recall the problem, right? The problem of the problem of expanded trimming, right? It's a setting where you have a graph, right? And then you have maybe a set U. Okay. And U here is expanding. So like you can send flow between any demand in U, you can send flow. But this is expanding in G. So the flow that you want to send between any two nodes inside U, it might go out. This is like a V minus U. Okay. And what we want is we want U to be expand inside U. That's the goal, right? Okay. So, okay, this is what we have. We have that U is phi expanding in G, but we hope it to be something like GU. Okay. Okay. Good. So what we're gonna do is to prune some part from U, right? We're gonna prune some part, like prune P. Okay. And then this is gonna be U prime. U prime is U minus P. And now U prime is gonna be expanding in U prime. So that's the goal. And today we only talk about, node weighting, which is degree. Okay. So the rule of thumb is that when you use push relabel, you usually can just work with degree node weighting. Okay. But by the end of the class, we try to still use push relabel, but make it work for anything. But for now, it's just work for degree. Okay. So when degree of G intersect U prime is expanding, it just means that this thing is expander. That's the definition. And okay, what we want also is that the new boundary of U prime here is still as big as the old boundary. Previously, we have without factor 2, the old algorithm we learned without factor 2, but here we're gonna relax it a bit. The size of the part that we prune should be small compared to the boundary. Okay. Usually, previously we have 2 over 5. Here we have 4 over 5. That's the goal. Okay. And the old algorithm, what was that, right? The old algorithm really just do this. You have the graph, and this is U. So what we try to do is just try to send max flow from the boundary to the degree inside U. So try to send flow from here, which is like degree, like boundary of U, and the sink is just degree in U, but scaled down by phi. So try to send things from the boundary to things here, but each of the guy can absorb only like degree, like only of its degree, but scale down. Okay. That's the algorithm, and just try to send this flow. If you succeed, you're done. If not, you get some cut. That cut, take that cut. If the mean cut looks like this, that's P, and then this is Q prime. That's it. That's the algorithm. And what's the point of this algorithm? The point was that we show that if, like, the point is that you're gonna get a flow, okay, such that if this is a battery, like this is, maybe this now is the new battery, okay, there's a flow that saturates the new, battery, like this is just the new battery that everyone here can send flow. And to this source, to this sink. Okay. So we prove that if we get the flow such that you can send from the battery, saturate the battery, and to the degree this part, then you're done. This is like what we prove. If we get this, if it used to be expanding in G before, and we get that from the battery, we can saturate the battery to this sink, then this is done. Okay. And the intuition is clear too, right? The intuition is that suppose that, okay, maybe, yeah. I just want to emphasize again that we want the flow that saturates the battery. Okay. Every edge in the battery is saturated. And why is that important? Because the intuition is clear. Like otherwise, there can be a sparse cut. Like if you can send flow successfully, if you look at any cut, then it will not be sparse, because if the cut looks like this, it was not sparse before, it's still not sparse. It's still expanding. If there is a cut here, well, there is a flow that try to send out of it. So this thing cannot be sparse. But if this flow, let's say you can only send it from some edges, but you don't send any flow here, then it can be the case that here, there is no edges at all, crossing S from U minus S. So, like, without flow, like, this set here, it used to be expanding in G. That is, there can be many edges here, right? But now it might not be expanding in U prime, because there might not be any edges from S to U prime. Because if you don't send flow, then there is no way to certify that. You see this intuition? Okay. That like the flow, to send flow from every edge is kind of the key to certify that there is no sparse cut. Okay, so that's basically what we want to do. Okay. We want to achieve this thing, to send flow from the battery, saturate everything in the battery, but without using max flow subroutine. Okay. If you run max flow subroutine, then the flow after the cut just like do that for you for free. But now we don't want to do that. Like we don't want to use this black box. Okay. Okay. So that's the goal. We want to avoid the black box and get fast algorithm. And the techniques that we learned today will give you some dynamic algorithms called expanded pruning, which is really influential. Like it's used in many dynamic algorithms, and I might give you some homework about this. Okay, so now let's talk about the algorithm. Okay, so the algorithm is that, let's start with some notation. Basically, you're gonna have a graph G, and you have some set C, some set U. Okay. In the beginning, like I gonna say that my alive vertices, the set of alive vertices is just U. Okay. This is a alive part. Okay. But basically, we'll try to do something that keep killing vertices. So the guy that alive, the set of alive vertices will shrink. Okay. And we will basically like work with the graph, some flow, some label, source and sink. That will only define on top of the alive part. So when I say that I shrink or I kill some set of vertices, then you just think like this, that I just, like suppose that I update a live set, then I just look at the new graph on a live node. The flow, let's say that, yeah, I kill something. Let's say I kill something here. Okay. The flow that, let's say that I construct some flow on a live part, then I'm just gonna restrict my flow on only the new alive part. The label too, and the sink, the source and sink as well. Just everything just restrict to the alive part. That's the, okay? Nothing tricky here. And I also gonna use the same notation that we will maintain some label of vertices, and Li is just the set of node at level I, L at least I, L less than I. This is just defined like before. Gcon is defined like before. It consists of edges. Once you fix the label, Gcon just consists of edges between consecutive level only. Okay. So far, so good. Okay, so now here's the algorithm. Okay. We do something similar to when we do push Relabel. Initialize zero label, zero flow. The sink is just the degree scaled down by 5. Parameter h, like before, something like log n over h, log n over 5. Okay. We have type h data structure. This is just like last class. Okay. And now I'm just gonna restrict my alive set to U. Okay. And here's the important part. I always like kind of set my source to be from the boundary of the alive set. Okay. This is intuitive because it's certainly what we want to do. We just want to saturate all edges from the boundary to the alive set. So this is just as expected. Okay. And here, good. This part is not surprising yet too. It's just the same. We just try to push and relabel vertices, the active node, like before, until every node with access is dead. Okay, just do that, like in push relabel. And suppose that there is no access, then I just say that I return my alive set as my U prime. Okay. And this makes total sense, right? Because if this is the case, it just means what? It means that we successfully send flow from the battery to inside the alive set. And we are done. We certify that U prime is expanding inside. So this is good. But what if we don't successfully send all the flow? Okay, so not all edges on the battery is saturated. Okay, like here, when this is the case, it means that when you look at the battery, you just saturate everything. But what if what if there is some excess? So you don't succeed in sending some flow on the battery. You don't succeed. Okay. So what I'm going to do is here. Okay. So this is just like last class. When you cannot send all the excess, there is some excess. And you set level H to be something like this, right? You can find a sparse cut in GCon. Okay. There are like, look at GCon, which has consecutive level. There are edges only between, like from level I to level I-1, I-2, and so on. There must be some sparse cut in GCon because there are many levels. So just find that. So let this be a sparse cut. So you have GCon, you have many level, H up to 0. GCon only have edges between this, only between consecutive level. Just find a sparse cut where like there are just few edges here. Like okay. This thing is sparse, like just 5 fraction. Okay. This is just like last class exactly. Okay. And then what I do is just I kill this guy. This is like kind of sparse. I kill it. So everything that remain alive is the level below I. Okay. And now I just do the same. Like I set my new goal, which is now this part is the new alive part. And so the new source should be just only from edges, the battery of the new, like the source is just the, like it just tries to send flow from the new battery. Okay. Is it clear so far? So observe that when at termination, we are just done. Like at termination, once we kill this thing, we just continue, try to send flow again. Okay? But what we do is just, I restrict myself, restrict flow, label, everything on the new alive part. And I just continue my algorithm. I don't restart it. I really just continue my, like the tight edge data structure. It's just from before, right? And tight edge data structure works because this is just to delete things. Tight edge data structure, you can just delete things and still continue running. This is the dynamic part. Okay? I just remove something and continue my push the level from here without restarting. Okay. And then maybe like when I continue this part, then maybe like now it's just gonna create like increased level again. And now maybe like some guy reach level H and there's still some excess. I just need to maybe find new sparse cut, kill, and then continue. Like it just keep continuing until at some point I keep running and there's no excess left. That's when you just return. But you see, when there is no excess left, right? When this thing happens, you are done. Because when you have no excess, it means that you successfully send this source, the battery from the alive set, to inside alive set. And we're just gonna use like the old, this old lemma which we proved before, that if you can saturate the battery to inside, then you certify expansion. Okay. So from now, I just gonna assume this now, that after termination, we know for sure that we are done. The expansion inside U prime is gonna be expanding inside U prime. Okay, because we get the flow that sent from battery of U prime to inside. Okay. So the expansion inside, we don't worry about it now. What we need to think is, does this algorithm even terminate? Right? And if it terminates, like we prune this part, like the part that we kill is the part that we prune. Is it too big? Is it small? That's the question. Okay. Okay. So, yeah. But I hope you see dynamicity of this algorithm. The point is you kill something and continue using the tight edge structure on the alive part. Yeah. Okay. Now, first, before we show the correctness, right? I need to like argue to you that like we never violate the invariant need by the push relabel algorithm. There are two things that we need all the time. That is, okay, we maintain some level, and this level L never overstretch any edge. This we need in our push relabel. Also, the flow that we maintain is always a pre-flow. That is, if you look at any node U, look at the net flow out of U. You don't send net flow out of U, it doesn't exceed the source from you. So like you don't pull mass out of nowhere. Okay? Just like you send at most the source. Okay. And if you look here at the algorithm, this part is just from push relabel. It never violates the invariant. We prove this. Okay. Where else can we violate? Like this is the queue. We queue something, and we do something here. We need to check here. Okay. When you queue something, can you overstretch any edge? No, you just remove things out. So there's nothing new. There's no new overstretched edge. Can there be like will it remain pre-flow? Yes, because we really just like, it used to be the case that for every node, to net flow out of you don't exceed the source. Now you just restrict yourself to a smaller set. So this is safe. What about here? Here you don't even you don't overstretch any new edge because you don't change L. But you need to check that it remains a pre-flow. Okay? Because here, this is non-trivial, a bit non-trivial to say that it's a pre-flow because you say like we cannot change the source set, right? We update the source. And we now need to say that once we change the source to this guy, the flow out of you don't exceed the new source. Okay. So let's verify this. That okay. Let's verify that when you add new battery source, F is still a free flow. Okay. So let's say that I draw this thing. Maybe okay. This is the part that we queue. Okay, and this is U. Okay, and U is here in the less than L part. This is a live node. And well, we just look into edges here. Yeah. And maybe the flow here is like 3 out of the capacity is 5, let's say. Okay. Maybe let's just look at one edge, just for simplicity. Okay. So it means what? If I kill this guy, then the flow into U would decrease by 3, right? Because like I just remove this edge, so the net flow into U decrease by 3, and you just sum over all edges like this. Okay, so the net flow into U decrease by 3, so it means that the net flow out of U increase by 3. Okay. But if you look at the new source of U, okay, the new source would increase by 5. The new source at U would increase by 5. Right? So maybe it's better to draw it like this. Let's say this is a live part. Okay. And this is my part that I queue. And yeah, maybe I draw it like this. There used to be the battery here, battery of alive. Okay, and this is node. Yeah. Okay, and this is part that I queue. Okay, this is not U. Okay. Good. And let's say here the flow is 3, but the capacity is 5. Okay. And let's say the capacity here is like a 5 and 5. Okay. So the old source at U is 10, right? Because the source at U just correspond to the old battery 10 here. Okay. But the new source at U is what? Now 15. Because when I remove this guy, this edge contribute to the source at U now. Is there a question here? Yeah.
I'm just a bit confused by how we're reasoning about F out being able to increase based on all of this, because I guess the way I'm thinking about this, it's just we have some flow coming in, which has to be less than the capacity, and then we're potentially removing some of those edges, but replacing them with source that is exactly the capacity if it's on the boundary. So I guess I'm confused about where the outflow is.
So this is net flow out of, like, it's the net flow out. So if you remove something that is in, it increases the net flow out.
Okay.
Right? Yeah. So you see, like, in this case, if there is just one edge from the part that I queue to U, the net flow out of U would increase by 3, but the source at U increased by 5. And it's going to be the case that, like, the total net flow is just at most the total source, like the source at U, that how much net flow increased compared to the source that increased, just because the flow is at most the capacity. Okay. So are we convinced that it remains a preflow. Good. Okay, so this is valid. Okay. Like basically think like for every if they are equal, then I don't add new unit of mass into the system. But if they are like off by 2, actually once I remove things, like I used to send 3. Now I kind of put 2 more unit of access on top at you. Okay? Okay, good. So this is the valid algorithm. It maintains the invariant that we need. Okay. So what about running time? Okay. I claim that the total time to find and queue the cut is just going to be linear time in total. The reason is that like what we do is just like we do sweep cut, right? And when we like there are levels, and when we like we keep like there are levels hash -1 and so on. And when we find like a cut that is like sparse in gcon, we just basically cut it, but the total time is just local in this part. And then so we spend time proportion to the number of edges incident to the cut. And then we continue, like when we need to cut again, we just kind of, do sweep cut again. So every edge is scanned by this process, like constant time, once basically. So the total time to queue all the thing is just linear. So that's nothing. But so the running time is just dominated by the tight edge data structure and push relabel. And that's like a mh log n, which is like last class. So that's why the running time is good. Okay. You see, the point is that you just run this thing kind of once, we don't restart. That's why it's just this running time. Okay, so now let's prove the correctness. We just left to prove 2 things that, like, okay, when you have you have you're gonna prune something, and the size of P is small, and also the new battery here, not too big. Okay. We don't want that like the bad thing that can happen, for example, is that what if we kind of keep killing things? Keep killing, and like basically we prune everything. That would be really bad. That can happen. I mean, potentially it can happen. We need to say that cannot happen. Okay. And the key to prove this is to look at this thing. I call it total source. Okay. So let's say that in the beginning, this is like initial source, just the source that we try to send from the battery of U. But what we're going to count is total source. This is like kind of total unit of mass that have ever appeared throughout the whole course of the algorithm. For example, like initially this thing is just the initial source, which is what, like just the size of U, the size of battery of U. But it can increase. When does it increase? For example, in this example here, right? When we delete this guy, this is when the total source increased by 2. Because I used to send 3 units here, but now I actually like said that I put 2 more excess on top of here. So like it keep increasing. The total source keep increasing. Okay. Okay. Let's see the example here. Suppose that this is a node, some node here. And I have this, I queue this guy. Now, E1 here would increase total source by 2. This is just like our previous example. But if you look at this edge, okay, but if the flow go in this direction, actually it would increase the total source by 6. Right, because kind of 1 unit actually go out of this. But how many unit of mass do I put here? I need to like cancel 1 unit and put more 5 units here. So actually I increase the total source by 6 for this edge. Does it make sense? And this is a kind of important concept that kind of we are keeping track of. Okay. Okay. So the idea is that when you kill someone, you basically kind of increase some total source along the battery here. Okay. And when we run another algorithm and kill something, we increase the total source here again. So this keep increasing, but we want to say that we don't increase by too much. Okay. And the key lemma is that the total source that we ever increase is just at most twice. At most twice of the initial source. Okay. And the initial source is of this size, so the total source is this. So why is this? Okay. Let's consider every time that we kill a cut, the sparse cut in GCon. Okay. How much total source, how much can it increase? So suppose in the simple case where, like that, the flow out of the cut is just saturated. So I mean that I have the part of the queue, and this is a live part. But it's the case that every edge go out, every edge that cross this cut actually is saturated in this direction. Every edge here, I saturate them, all of them. Okay. Suppose that's the case. It will not happen, but suppose that all edges from like level at least I to less than I are saturated in the direction from this side to this side. Then you see that in this case, we don't need to add any new mass. It would not increase at all. Is it? Do you see this? Like, I need to stress here. Like, this is just important. Any question about this? Is the concept clear or not really? Seems everyone is confusing. So yeah, is it okay? Or yes or no? Okay, ask question. Yeah.
So this is a case when like all the edges are saturated.
Yeah. So
Like we delete an edge, or we delete a bunch of edges, but we aren't adding any extra like
yeah,
source because like it's already all of the source they could carry.
right. So like it's like this node here, right? Maybe the source there are, like this is just the part that we kill, but there are like boundary outside this thing too. This is a live part. Okay? And the total source at U could be, if this is 5, this is 5. The total source at U used to be 10. But now, like, if I delete this guy, once I remove the part that I kill, and let's say the capacity here is 5, then the new source at U would become 15. Right? But if the flow from here is saturated, like I send 5 units of flow here too, right? Then think how should I think? How should you think like this? Like it's like there are 5 units of flow here, and now it just become excess here, become like the source. I just move this thing to here. So I don't need to add any new mass into the system. It just used to be crossing this thing. Now it's just here. Yeah. Okay. Yeah.
Is the intuition we should be having here is like because this ends up being a sparse cut, we should be like pretty close to all of the edges being saturated?
Exactly. Like if we because this thing is a sparse cut, basically almost all edges are already saturated. Yeah. Okay. But this is just important. Like if this is all saturated, you don't increase the total source. Okay. But okay, in general, it's not the case. In general, like you actually send flow out of this guy. You don't saturate everything, but you basically saturate the cut, almost all the cut, but you are off by this much, just from last time. Okay. Why? Because this is the only edges on the consecutive level that you don't saturate them. This is the edge on the consecutive level that the flow might not be saturated, or it might not. It might even go in the wrong direction. So this is like how much you don't saturate the flow, the cut. How much flow that you don't saturate this cut is by this much, 2 times like the size of the cut in Gcon. So it means that, so this part that we don't saturate, let's say there is some edge here, and like the flow is 0, but the capacity is 5. Then basically I just gonna increase like a 5 unit of things here after deleting. So it means that the total source can increase by basically this one. But we choose, this is a sparse cut in Gcon. So this thing is small. We choose this is sparse cut in Gcon, so this is small. Like small, something like 5/10 over something you can choose. But this is small. So now the point is when you cut L at least I, you add something like the volume of L at least I times phi over 4. Okay. 4 here is important. I can choose this 4 to be something tiny, like 10, but 4 is enough. Okay. But you see that whenever I Q this L at least I, okay, this many unit of mass, the sink at Li is basically Q together with L at least I. Because I really just, everyone here is fully absorbed. And I just remove it from my system, never look at it again. Okay? I'm gonna Q at least this much. Okay? So it means what? What's going on here? It means that, okay, you see this, right? When I Q this guy, everything in this L at least I is fully absorbed, and I just remove this many unit. Okay. So it means what? I can add something, but whenever I add something, I remove twice of that from the system. Okay. So, like, if I start with like a n thing, and I said whenever I add something, I Q 2 of them. Whenever I add something, I Q 2 of them. What's the total number of things at the end? It looks like basically this is like the total number of nodes at the end. If you start with like n nodes, at the end it can be 2n minus 1. Okay, so the same reasoning, like whenever I add anything here, I remove twice of that. So at the end, it means that the total number of mass that I ever put into the system is just at most twice of my initial mass. So when we add 1 unit, we Q 2. So the total unit that we ever the total number of unit is just at most twice of initial unit. Okay. Good. So now we are almost done. Like, once you bound the total number of like unit of mass that we ever put into the system, we are basically done. Why? Because I claim that the degree of P scaled down is at most the total of mass, which means that like the volume of P is at most like something like 4 or 5 times this thing. And why is that? Well, because like P is the part that you prune. You prune some P, you prune. Every part that you prune here, right? The sink at P are saturated by the mass from the source. Like everything here that you prune out, the sink capacity of it is from the is from some mass. So the total sink of P is bounded by the total mass that ever created. But what's the sink capacity at P? It's just degree of P scaled down by phi. So just combine this together, you get this. Okay. So the intuition is here is just, you know that no matter what, the total unit of mass that you put through the system is bounded. But every time that you remove something, that also remove, like you can charge it to the mass that you put into the system. Like the sink, like every time that you QP, you kill the sink there, right? Okay. Okay. And lastly, the battery. The battery here is at most the total mass. Why? Because, well, like, just look at the source at the end. The source at the very end is just the battery of your U prime, right? So it means that the size of the source, the size of total source at the end is just your size of the battery of U prime. But the total source at the end is just part of the total mass that you ever created. So you get that this thing is at most the total mass ever created. So this is the new battery is at most twice of the old battery. So we are done. So you see that like once you buy the total source here, you're done. But like I'm not sure that you get this. It seems from your face you are confused or something. So yeah, And so now, but now we are done. Like we just show the fast algorithm that you see like that just do exponent trimming. Okay, so questions.